significantly with all this work, so I still want to give her props. She's an energy specialist here at EQ. For those who are unfamiliar with us, we are a Toronto-based multidisciplinary firm with our primary focus on multi-unit residential buildings. We also do institutional and commercial work. We do energy and carbon analysis, sustainability, and commissioning as well. So background on this conversation. So with decarbonization kind of at the forefront of sustainability, we found ourselves asking, how can we optimize operational and embodied carbon with an eye on whole building life cycle carbon? What's stopping us from doing this? Where are the gaps in knowledge, information, and processes? And what's in store for the future? Where are we going, and what impacts might grid electrification have on a warming climate and the decisions we make about our buildings today? Why do we think we should do this work? With traditional design, operational is typically the driving force between looking at lifetime carbon. But as we move to low carbon operational design, operational becomes a much smaller piece of the lifetime carbon picture. Additionally, Embodied is growing significantly within our industry, and there are lots of resources for very, very high performing buildings, but not as much as the things in between. And there's also not too much on mixing operational and Embodied together. So we wanted to look at that with a focus on mass improvements for the broader market and also highlight opportunities for high achievers as well. A bit of an agenda for our session is introduce the archetype building we used, look at what was evaluated, what are the results, what impact does MEP, so mechanical, electrical, plumbing, have, and what should we take away from this? So starting with our archetype, this is what it looked like. It's a 24-story multi-unit residential building, pretty typical representative. It has fan coils, a 4-pipe fan coil system in the suites with heat recovery, precast and spandrel envelope, about 60% precast, 40% window wall spandrel. It's not shown in this rendering here, but about half of the perimeter of the building was balconies as well, so significant balcony areas. It had traditional gas boilers with a centrifugal chiller. The wall performance with thermal bridging was about an R5.5, which is pretty typical for the Toronto market. It had about a 40% window wall ratio with traditional double glazing. This project did pursue LEED 2009 certification, got 10 points. So, and it has recently occupied. So we were able to use like the as-built building or as-built drawings to do all of this analysis. A note on our methodology. So we used a 60-year building life cycle based on ZCB recommendations. We derated our assemblies using the BC Hydro Thermal Bridging Guide, which is pretty industry standard without doing like project-specific 2D or 3D modeling. Our preferred energy modeling system is Energy Plus version 9.6, and we use standard modeling practices under both LEED and the Zero Carbon Building Standard. Our embodied calculations were using one-click LCA and used ZCB methodology. We also used the newly released MEP plugin on one-click LCA to investigate that portion. And we also excluded capital costs from the analysis. Capital costs are super important. We totally understand that. But due to the number of iterations we looked at on this project and how much capital costs seem to fluctuate month to month, it just wasn't realistically feasible for us to include that. So while we may be able to make some commentary on like, you know, this might be more expensive or things, we can't give exact trade-offs. For the work, we looked at 3 locations. We wanted to look at as much as we could and how things could impact things. So how can location and your carbon grid intensity impact things as well? So we chose Toronto, Calgary, and Vancouver. Calgary because it is very cold and has a very carbon-rich grid for electricity. Vancouver was kind of the opposite end of the spectrum, quite mild and has a low carbon grid. And then Ontario is kind of somewhere in the middle. So it has moderate climate and a moderate climate grid compared to the other 2. What did we look at? So going through this a little quickly so we can get into the meat, but we looked at opaque wall and vision improvements. So like shifting away from a spandrel window wall system to like a true wall. We did thermal bridging analysis as well. The opaque walls we looked at ranged from about R5 to R20 overall effective performance. We looked at different insulation types, looking at metal versus non-metal framing and triple glazing, reducing balconies. On the HVAC side, we looked at the baseline fan coil system. We also looked at air source heat pumps and air source VRF and geothermal, and looked at both gas and electric backup options. We looked at reducing the corridor ventilation rates from 30 to 15 CFM per door. It doesn't impact the operational or the embodied carbon, but corridor ventilation can be up to half the heating loads in a MURB building. There can be design implications to going all the way down to 15 CFM per door, like weather stripping, recirculating range hoods, or ductless dryers, but it can have significant impact, so we included it. We also looked at increasing efficiencies for the ERVs from 70 to 80%, which might require using a remote ERV. Low flow plumbing fixtures. For concrete materiality, we looked at various SCM concrete mixes while keeping in mind cure times as well, especially for the above grade components. And for the parking reductions, we also looked at how much impact that had with the elimination of parking minimums in a lot of jurisdictions. It's something that can be on the table for a lot of projects and is an easy way to reduce embodied carbon. Before jumping into the results, I just wanted to kind of highlight a little bit on the opaque wall further. So our current design is kind of like a nominal R20, which is this full bar, and gets derated to this dark blue, the R5.5. When we looked at our fully optimized assembly, keeping those balconies in there, you know, significantly impact. This yellow is the balconies. So just showing the impact of the thermal bridging on these calculations, it can have a big detail. And I know most of us are probably from Toronto, and a lot of us are very familiar with this from the Toronto Green Standard. But there are a lot of projects that don't have these requirements. It's not required under a lot of building codes, and many architects and designers are still unfamiliar with the true impact of the envelopes they're designing. So just communicating with clients about the impact of balconies and other thermal bridges on their performance, especially when they're looking at high performance envelopes, is really key to helping performance. So with that all in mind, what are our results? I'm going to pass this to Anna quickly to start off an embodied, and then we'll move back over to operational.
So here are the results of the archetype building for embodied, and these numbers are represented in kilograms of CO2 per square meter of GFA, and where the GFA is selected based on our methodology that aligns with the NRCan guidelines for whole building life cycle assessment, and that's what's currently referenced in TGS, which follows this FCB guidance as well. In our experience, this is quite representative of a concrete form MURB in Toronto, where structure is approximately 60% of the carbon. And in that 60%, concrete represents 75%, and the rebar represents the remaining 25%, with the largest contributors being above grade slabs and shear walls. Foundation and below grade slabs account for 15% of the structural impact, which is in line with the building with approximately 2 floors of underground parking. And there's really no other major takeaways from the envelope breakdown other than that the building is primarily spandrel and window wall, so these two assemblies were the most impactful. However, the precast assembly was almost double the embodied carbon intensity per square meter of enclosure than the spandrel. Next slide. So from that baseline, we investigated the impacts to embodied carbon based on the optimizations to the envelope, glazing, parking reduction, balcony reduction, and concrete mix materiality selection. So from the spandrel baseline, we started with a 5-inch industry average heavy density mineral wool board for insulation between the studs, and upgraded that to a 3-inch closed cell spray foam with HFO blowing agent, specifically wall tight, delivering the same U value with an overall lowered embodied carbon intensity. For precast, we started with 4 inches of continuous mineral wool insulation board and 3.5 inches of mineral fiber bat between the studs, and this was improved to 4 inches of continuous of the same wall tight spray foam. Glazing changes represented a switch to a fiberglass frame from an aluminum frame, unitized double glazed window wall. And the next was that parking grade, below grade parking was limited. Balconies also represented, we removed the balconies here, and that reduced the concrete floor slabs and reduced 3% of the substructure from the load change. And concrete mix optimization from the baseline on industry average baseline was defined by the Ontario Concrete Industry EPD, and roughly that accounted for a 20% reduction from baseline, and that we used Lafarge's EcoPact Prime concrete. We then ran the same assessment for Vancouver and Calgary, where in Vancouver the results differed only within 5%, and therefore we're showing the Calgary results next. So Calgary embodied carbon results started at a much higher total embodied carbon density due to the grid mix, raw material transport distance, local industrial processes, and regulatory environments surrounding manufacturer policies. Overall, the base design and optimized design are roughly 25% higher than Toronto and Vancouver, with the delta in reduction compared to Toronto in categories of parking, balconies, and concrete mix for the reasons previously mentioned. One thing to note here is that due to the limited amount of regional specific EPDs we have at this point, the main differences between Toronto and Calgary runs are regional concrete rebar percentages estimated at 75% recycled content versus 95% recycled content in Toronto. And each envelope material where available has been selected for a regional specific material to the extent of available EPDs. So similar to Toronto, prioritizing concrete materiality selection is the simplest bullet to carbon reductions when comparing with the Ontario baseline. Next.
All right, switching quickly to the operational results. I just wanted to show our internal gator tool, we call it. This is kind of what we use to visualize all of our inputs. We did over 13,000 simulations for this project, and this helps us filter all the results to see how the different measures all interacted together so we could really optimize the design. Hopping into Toronto first. So our base design had a carbon intensity operational of 23.6. And if we fully optimized the design, we got down to 4. So prioritizing envelope and passive measures can lead to significant reductions as seen on here, like moving away from the window wall, increasing insulation, and improving the glazing performance. Though as expected, electrification and mechanical improvements led to the biggest reductions, with tech like heat pumps being both high efficiency and incorporating fuel switching, with Toronto having a fairly moderate carbon intensity for electricity. We saw notable changes here. So overall, we saw about an 80% reduction in operational carbon with these measures. If we switch to Calgary, which is more carbon intense, you can see our starting point is significantly higher, about 50% higher at 35.9, the same design. Similar to Toronto, we do see notable changes with passive improvements, but the biggest change is still from doing a fuel switch. Even in a more carbon intense grid, it's still less carbon intense than than natural gas, and still connects with higher efficiency systems, which help reduce our carbon. With these same measures, though, we were only able to see about a 50% reduction at the end of the day instead of an 80% reduction that we saw in Toronto. If we go to Vancouver, our starting point drops to 17.6. So our starting point in Vancouver is only slightly higher than our optimized design in Calgary, just to show how big of an impact climate and the grid can have. So in Vancouver, we were able to see an over 90% reduction in carbon. Again, similarly for each category, the relative savings were pretty similar, with the biggest savings coming from a fuel switch. We overall saw the fuel switch was a minimum 40% improvement, greater in Vancouver, with the envelope leading to about a 15 to 30% reduction in carbon, depending on the climate. So digging into how operational and embodied go together, let's start by looking at our envelope options. So when we start talking about the envelope, we really want to talk about material selection, especially for our insulation. So this chart kind of shows the thermal performance and the carbon performance of various insulations. And if you kind of think of it as green is good and red is bad, you can see it's kind of a mixed selection here. Open cell spray foam does perform the best on here. And that's mainly because products with HFC blowing agents have been banned from being manufactured since January 1st, 2021, which resulted in the adoption of HFO blowing agents, had a much lower global warming potential. Since this change, insulations like spray foam and XPS, which used to be considered a bit of a mixed bag in terms of choice because of its great performance and not great embodied, now are really good options to consider, especially due to their high R values. These are not the only things to consider when looking at your insulation, though. We're not going to get into it too much, but going off of spray foam, obviously combustibility can have a big impact on what insulation you're selecting, especially with spray foam. I do know at least one architect who said that their insurance will not cover the use of spray foam in their building, so alternatives would have to be selected. Other things to consider include the physical space that you have in your building, how thick your wall can be, any condensation concerns, capital costs, thermal degradation over time, acoustics, and the ability to retrofit in the future. Looking at how these things go together, I'm going to display some data from Toronto because we saw similar results in the other jurisdictions. But with these operational improvements, opaque wall and glazing added up to about a 20% reduction in your operational carbon. When we layer the embodied on there, if we do a like-for-like comparison, we saw about an 11% increase in embodied carbon. Again, this is with like-for-like things, so keeping the same insulation, but just making it thicker, or keeping aluminum framing, but adding a third pane of glass. If we're able to optimize the design a little bit more, we can see more improvements. So if we can swap out the insulation type or switch to fiberglass or other non-metal framing, we only saw a 5% increase. So that's a pretty big reduction. And then depending on how the design is optimized, this could be decreased even further. This graph represents kind of like the best performance that we were looking at for operational, but there are diminishing returns on things like R values. So, we evaluated up to about an R22. You might not need R22 in your project. Maybe you can do an R15 or 18, still see significant operational savings, but not take nearly as much of a hit on the embodied side. Glazing is also really interesting to look at. As double versus triple glazing and metal and non-metal framing all have significant impacts on lifetime carbon. So looking at triple glazing specifically, if we have a gas baseline, which the majority of projects outside a couple major cities have, triple glazing, we saw about a 10-year carbon payback. So that's how many years of operational savings we needed to offset the embodied carbon premium. With triple glazing, there is an additional pane of glass and thicker framing, which is what's causing that embodied premium. With the gas baseline, if we switch to fiberglass, we got instant lifetime carbon savings. It's not feasible on every project, but it's something worth considering. I'm showing information for Calgary in this slide because it had the shortest payback due to its grid mix. Toronto and Vancouver had similar paybacks, it was about 13% higher, like under 12 years, which is still pretty good. So this is using a gas baseline though. If we are looking at an electric baseline, the story changes quite a bit. So if the baseline is electricity, that 10-year payback jumps to 26 years in Calgary, and in Toronto and Vancouver increases to over 100 years. In those scenarios, the carbon payback is likely going to exceed the lifetime of the glazing itself and essentially eliminate the potential for lifetime carbon savings. In an all-electric scenario as well, fiberglass and aluminum framing had similar carbon paybacks just due to how much lower your carbon intensity was with electricity. There are other benefits, obviously, to triple glazing, like thermal comfort and other things, but just looking at operational versus embodied, these were the differences that we saw. I'm now going to pass it back to Anna to talk a bit about our concrete that we might be using on our projects.
Yeah, so we limited changes to structural as there are some challenges to building alternative structure projects that slow market adoption. So, for example, in the case of hybrid or encapsulated mass timber structures, code limitations on building height can exclude projects that need specific density, and insurance premiums can be expensive and account for over 40% of the overall construction premium. And the design and construction process requires certain specialized consultants and builders and likely costly collaborative project delivery methods, which not every project has access to. So for those reasons, alternative structures may not be feasible for every project, and therefore this assessment looks into optimizations for projects without that kind of structural flexibility. However, as a rule of thumb, based on our experience from steel and hybrid mass timber structures, there is a 15 to 40% savings on overall embodied carbon perspective compared to a concrete form structure. So for projects limited to concrete structure, let's compare the impacts of materiality versus a limited structural design change. Next slide. So we limited the structural design changes to balconies and underground parking, as these are both really gaining traction with our clients for both operational and embodied carbon. When we compare those two improvement packages in Toronto, improvement changes ranged from 6 to 12% in Toronto and 9 to 16% in Calgary for overall embodied carbon reduction. In Toronto, the below grade reduction of one floor made up for 5% of the impact, while the other 0.75 was from the 25% balcony reduction. In Calgary and Vancouver, similar ratios existed. However, Calgary's percentages were higher due to the greater impact structure as on the overall embodied carbon. In the optimal improvement case, the removal of 2 parking floors, so no below grade parking at all, only increased the savings by only 1%, while removing all balconies resulted in a 3% reduction. So for buildings with 1 parking level below grade, this is almost as good as no parking below grade, as there is no additional below grade slabs beyond your foundation slab. And under conservative improvements, it's about kind of ensuring that we're discussing with our concrete suppliers for the optimal mix type and considering aspects of slag while balancing for drying times, winter mixes, or high early concrete with accelerators. These packages are a simplified summary. So as you see, the conservative and optimal improvements are packages of simplified summaries of concrete mixes proposed for a project targeting 10 to 15% savings, while also selecting for the best insulation products with EPDs. With these minor adjustments, a project may already save 14% from baseline, which already exceeds the optimal improvement package in concrete limited design changes that we showed previously. One thing to point out is that the upgrade in insulation between the 2 packages only accounts for approximately a 4% improvement between the 2 packages. So with the remaining of each package attributed to the mix design, the point of that is really consider your mix design early on. So this slide concludes that concrete materiality can have almost twice the impact than limited design changes. Not to say that design changes are important, but embodied carbon reduction or ZCB are still worth looking into for projects with really fixed structures. So what impact do renovations have? So replacements and renovations, that language comes from LEED, that renovation word, but it's really like replacements. They need to be considered within the life cycle of a building. So in a MURB, likely the most impactful replacement to embodied carbon in operation are the IGU replacements. So in a MURB, the IGUs likely need to be replaced every 15 to 20 years or so. And spandrel or precast systems likely should last the 60 years of the assumed lifespan of the building or longer. However, they would require work around resealing at the joints, potential for thermal insulation upgrades, replacement of damaged panels, or addressing any major thermal bridging issues. Therefore, LEED v5 has proposed a 0.25 factor for renovations every 10 years to address some of these changes. And you can see that the changes or the results based on our base building can add up to 35% over the span of 60 years when we're accounting for that 0.25 factor. But preliminary draft phrasing seems focused on interior finish renovations and not just envelope or MEP replacements and retrofits. So I guess take that 0.25 factor with a grain of salt. Over the life of the building, though, this can have a really notable impact on lifetime carbon and shouldn't be discounted. So some of our key takeaways are operational savings measures can sometimes conflict with embodied carbon reductions. So for example, our insulation, material selection, or triple glazing. With material selections, like there's 100 ways that you can achieve a specific R value for a wall. So be mindful of which insulation you choose. In assembly design, it really matters where you place it, how you design your building to reduce thermal bridges. So like a 3-inch insulation in a back pan is not nearly as effective as a 3-inch insulation between thermally broken clips. And consider the reduction of balconies as an option for both operational and embodied. And replacement and refurbishment, while not currently being accounted for in most LCAs, the replacement of an envelope can have a really large impact on lifetime carbon. So good idea to consider that. So the next slide is, we're just going to discuss what impact MEP would have on this assessment. So MEP is a large part of our embodied carbon discussion. An ARUP study actually in 2023 estimated that it could add somewhere between 15% to 20% to a residential building's upfront carbon from A1 to A5. And so we included it within our embodied carbon analysis. And LEED V5 does have a proposed MEP factor, which combines it with interiors and furnishings, and that's a 0.5 factor on your overall embodied carbon. While this factor is an MEP and insulation, it does a pretty good job of bringing to attention the impact that this system has on embodied carbon. So we wanted to compare the results of this factor to the MEP study we completed for our archetype building and alternative MEP designs. Next slide. So we ran an MEP analysis using the one-click LCA MEP tool, where every piece of equipment from the mechanical schedule was included in addition to their distribution systems. So just as an example of what that might look like, in a heating and cooling system, that would include the vertical mains and on-floor horizontal distribution, HDP, and brass fittings, as well as insulation to the pipes, while all pumps and boilers and chillers were separately added. So on the chart you see here, we've categorized an MEP low, that is the gas fan coil unit building, and an MEP high, which was the air source VRF. As we'll see on the next slide, it's actually the lowest embodied carbon of all the systems. But for our baseline building, this represents somewhere between 30 to 60% increase in embodied carbon. We can see here that comparatively, the 0.5 factor, which is also meant to include interiors, would actually underestimate the impact of MEP in the system. However, MURBs are much more equipment dense with ventilation and HVAC systems in each suite for tenant control. So this may lead MURBs to have a higher proportion of MEP for embodied carbon. So what systems did we actually assess? Next slide. So we ran the MEP assessment for 5 of the most popular mechanical systems in MURBs in Toronto to understand the scale of the difference between them. The results showed that the better performing operationally, generally the higher the MEP intensity, with air source VRF as the highest embodied carbon, primarily due to refrigerant leakage contribution. So in Toronto, because of our relatively clean electrical grid, fuel switching has the greatest potential to greenhouse gas emission reductions over the lifespan of a building. But just to note, these numbers are just a snapshot of MEP of the building today based on current emission factors, not based on future projection models by organizations like ACC or NREL in the States. However, if we were to take a look into these numbers and how they would change over future years, we're anticipating a sharper decline in emissions factors for electricity due to zero emission sources such as onshore wind, small modular reactors, and continued use of hydro. Natural gas emission factors are also expected to decline due to tech improvements and regulatory measures. Next slide. So breaking down those 5 factors into the categories of A1 to D, a key outlier here is the refrigerant leakage within air source VRF. So when we talk about refrigerants and refrigerant leakage, your system type really matters. So it turns out that the most factory charged pieces of equipment, like chillers or self-contained heat pumps, tend to leak less than field installed equipment that have large refrigerant lines that go from the evaporator to the condenser. Another consideration for refrigerant leakage is that there is no drop-in replacement for your equipment. And then at the end of the life, you may want to abandon that system due to phasing out of current high GWP refrigerants. Therefore, it's important to consider, and we review for refrigerant type and replacement opportunity and adjust for refrigerant leakage and volume within your mechanical architecture. There are several standards for this leakage rate. However, a promising one that came out recently was the ASHRAE 240P refrigerant section. And this would introduce a blended rate for service life, annual leakage, and end-of-life leakage from numerous sources. So not to say that VRF is not feasible, but consider VRF systems with lower GWP refrigerants, such as R134A with a 100-year GWP of 1430. Or better yet, there's also R1233ZD with a 100-year GWP of 5. Next slide. So to consider Toronto as the middle ground of a moderately low carbon grid and also a moderate climate, that allows it to have kind of the greatest advantage with air source VRF, which has the most absolute carbon savings. So approximately 15% more tons of carbon saved on low carbon, warm Vancouver versus like the cold, high carbon Calgary. So this leads to a lower carbon payback. While air source VRF is highly efficient operationally, as previously discussed, the high refrigerant charges lead to higher embodied carbon with a system lifespan payback of 9.6 years. So in comparison, air source heat pumps have a similar operational savings, but only have a 3 to 4 year carbon payback. So when we're balancing those two systems, it makes sense that air source VRF or air source heat pumps may come on top of air source VRF. So in this conversation, it's important to consider that also government policies, carbon pricing, and incentives for low carbon tech can affect the cost and payback period for altering carbon economic incentives and operational parameters. So institutions such as CMHC, RBC, BMO, or TD all offer versions of green mortgages where the carbon payback may change for developers who have access to savings on insurance premiums. So what are our key takeaways from MEP? So MEP are orders of magnitude from different, between different mechanical system types. So really be careful and consider MEP early on in your project. Again, while not currently accounted for in most LCAs, replacement of MEP equipment may account for somewhere between 30 to 60% of the impact on a MURB. MURBs have much different MEP requirements compared to offices or other archetypes, as there's typically more equipment and a higher burden on domestic water. Those MEP systems can be costly and difficult to retrofit, and doing electric all electric from day one is ideal in most cases. However, we need to balance that refrigerant selection and quantity. And last but not least, the refrigerant calculations should really be done as early as possible and consider the longevity of your recharge equipment from your end of life. So
Thanks,
I'll hand
Anna.
it back to Sam.
So what should we take away from this? We've broken down the results that we just discussed and tried to create 3 packages to help reduce whole building lifecycle carbon. The first includes easy to implement measures that we think the majority of projects should be able to easily incorporate into their projects. The second is an optimized performance, where if you have some more design flexibility, here are some things that should be able to help. And the third is kind of our optimized scenario. So looking at the easy to implement measures, we were thinking, or we were planning on incorporating reducing your balcony areas by 50%. So on this project, that led to about 25% of your perimeter having balconies on it. So you could still potentially have a small balcony for each suite or the majority of suites. We switched away from a window wall assembly to a true like panelized assembly, like a metal panel. For reference, we had an R about 5 assembly in the base. This is improving it to an R9 effective, and being smart about your insulation selection. Looked at low flow plumbing fixtures, improving your ERV efficiency, and reducing your corridor ventilation rates. We also had some conservative materiality selection. We didn't make any changes in your MEP here, so this is still an all gas baseline. But even keeping that gas baseline and putting these easy to implement measures in, we saw an approximate 20% reduction in life cycle or lifetime carbon. If you're able to go a step further and have a bit more flexibility in your design, these are where we think you might be able to hit. So the additional measures we did was either keeping that kind of R9 performance target and removing balconies completely to improve your assembly, or keeping those balconies in, but improving your overall performance in other ways to R about 14, may lead to thicker walls or other changes, but still not top of the line envelope. We kept double glazing, but switched to non-metal framing, which there can be design considerations like fire code limitations, but if you can, it's great on both operational and embodied carbon. We reduced the window wall ratio to in the 30 to 35% range, which we have seen quite a few condos in Toronto starting to do. Using a higher SCM mix, which can require longer cure times below grade, and removing one level of the underground parking. So that in this scenario, it was a 50% reduction. We also had some partial electrification for the air source heat pump. So not necessarily on the heating and domestic side, just on one of them to help reduce that. That led to a slight increase in MEP, but notable reductions on the operational and embodied side. And combined, these measures worked out to about a 35 to 45% lifetime carbon savings. It was a little less in Calgary as the fuel switch was less effective with the carbon intense grid. And then kind of our best scenario that we were looking at is if we threw everything we thought that was great at the design. So building on top of those previous packages, we fully eliminated the balconies. We fully switched to air source heat pumps with electric backup for both heating and domestic systems. We removed all of the underground parking and optimized our materiality. So again, slight increase on the MEP side and a little bit of a change in the embodied, but these changes resulted in about 40 to 55% lifetime carbon reductions from our starting point. So you can see some pretty significant impacts on the design. Now, just before we give our final notes, we do want to bring up a couple things that can influence these things, like the grid. So the Government of Canada did some projections as part of the Canada Energy Futures Report that was published in 2023. So if these blue lines are our baseline design and green is our optimized design, the dashed lines being the projected carbon. In Ontario, the grid was anticipated to get cleaner. So naturally, our buildings are just going to use less carbon. Whereas in Alberta and BC, their grids are projected to stay fairly similar to what they are today. Our carbon use is heavily dependent on our grids and can amplify the impact of individual buildings and help naturally reduce carbon in existing buildings. While some forecasting is available, it's obviously subject to change. Like a more local example to Toronto is the somewhat recent decision, to refurbish instead of close the Pickering nuclear plant. And we should just try to do as much as we can on an individual project basis, but keeping in mind, we also need to advocate for decarbonization of our grid as a whole because it can significantly impact our goals. Another thing to consider is the climate. So we're looking to see a 25 to 35% reduction in heating degree days over the next few years, like 60. So warmer climates will shift operational performance to be less dominated by heating loads. That means that non-heating loads will be a bigger piece of the pie. And for existing buildings, energy use and carbon will naturally decrease, which hopefully will lead to easier retrofit opportunities as equipment sizes don't need to be as large. And then just our final thoughts. So with significant constraints, you can still see some pretty notable impacts, like at least 20%. We saw up to 60% with some of the things we were looking at. And the best time to evaluate design decisions for both operational and embodied together is early in the design process. Even when that hasn't happened, though, you still can make some design decisions that should be able to significantly help. Operational carbon saving measures can sometimes conflict with embodied carbon reductions, and running these analyses concurrently is really important. MEP is finally coming into the picture, but there is definitely more research required. A lot of the stuff is fairly preliminary. There's not necessarily EPDs available for everything. And MURBs specifically are much more HVAC dense than a lot of other system types. So hopefully there will be additional research done into that to see how big of a change there is between MURBs and other system types. One thing that was very clear as we undertook all of this analysis is that we need more EPD information. Adding EPD requirements into specs can help encourage market adoption and just try to get you the most accurate information possible. And then just on a more broadly speaking point, getting more benchmarking information on both operational and embodied carbon can go a long way in helping us understand the environmental impact of the built environment, even if it's anonymized. I know Toronto recently passed a law or a bylaw about embodied or operational carbon analysis, or not operational carbon, benchmarking. And they're working on some embodied carbon stuff, I know, through a recent RFP. So hopefully that all gets public and we can all share and learn from each other. That's all we had for today. We wanted to build in a little bit of time for questions. Yeah, thank you for listening. Any questions?
Sorry, I was muted, but if you have any questions, please put them in the chat or unmute yourself and ask questions. I will ask, are you having a lot of these conversations with your your clients so far? Like, do you find that they are getting pretty savvy about it, or is it still more of an uphill climb and an education?
I find it really
situation?
is hit or miss depending on the client. We do have some that I would say are more leaders that are starting to look at both operational and embodied together and really having that conversation. We do have some others that yet still talking about the full effect of thermal bridging is a lot, or just getting them to start doing that embodied conversation can be there. But I find that it is for people we do have to have that conversation with. It's becoming an easier conversation, which is nice.
Yeah, good.
Yeah, I'd agree with that. I think the industry is catching up. There are some leaders right now, maybe they're driven by some shareholder demands, and also maybe their investments are fueled by certain carbon targets. And so yeah, we're seeing certainly a lot of that. It's still within the lead realm, a lot of our embodied carbon work or ZCB driven, but certainly more drivers are coming in to fuel the developers to think about it more.
Yeah,
Yeah.
I know Mississauga, their recently approved green development standards will have an embodied carbon analysis as part of the minimum requirements for all buildings. I'm a little hopeful that will come to Toronto as well, but hopefully that becomes a wider thing going forward.
Yeah. Maru, you have your hand up?
Yeah, thank you so much for the wonderful presentation. It was very insightful. So, my question is about the uncertainty of the embodied carbon emission. So, have you looked into the uncertainty of the data? For example, if you are extracting the data from the BOQ, then maybe the quantity consumed on the site may be variable. So, have you considered the waste generated on site also?
Sorry, could you repeat your question one more time? As the waste
Yeah.
generated on site, was that considered within the
Uh,
calculation?
So uncertainty, usually when you collect the data from the BOQs or from the site actually. So did you consider some sort of uncertainty like the waste generation generated on site?
Yeah, so it's more of a schematic level or like design development early LCA that we were doing. For the archetype, like the idea of this is to apply general rules across future LCAs and develop sort of rules of thumb. So for example, that MEP slide where we compared the 5 systems, those are just like they were orders of magnitude different from each other. So to find those rules of thumb between them. However, like our actual model was from KIP2, which is a real project that's already been built. So we took EPDs sourced from the subcontractors. We took exact material quantities from the project. And it's as close to a full as-built LCA as you can really get. So I think that if that answers your question.
Yeah, that's
We
exactly
were able to
what I
take
was looking for.
Yeah, we were able to
Yeah.
take exact as-built quantities.
Because usually what happens that sometimes the teams are not aligned, so you may have some gaps in the data collection.
Yeah,
So
absolutely.
you were able to manage all the EPDs, or there were third-party data also, like average data you have considered?
Yeah, so we did consider some most of the materials input are from real EPDs. Some of them are just from standard one-click standard EPDs. However, wherever possible, we took it from where the subcontractors had given us exactly which material they used. But there's a lot of materials without EPDs. EPD availability is a big problem still right now, so we have to kind of do the best that we can with what's available.
Yeah, so did you also consider, let's just say, for the project we have 100% of the material. So out of the 100% material, what was the percentage of the EPD you have got? And you might have scoped up some of the material because of unavailability of the data, right?
Yeah, I would say a lot of the finishes we have a lot of great EPD data for, so that was available. Most of the insulation was completely from the EPDs. For the concrete, it was the Ontario Baseline EPD concrete EPD. Many of the other ones, like for example, the steel studs, that was a baseline one. Some of the roof assemblies we had to make some assumptions on. But generally, if I had to give a number, maybe like 60 to 70% are from real EPDs, and the rest of it is estimates.
Yeah, that's a really good number, I would say. Yeah, I think that's all from my side. Thanks.
So we have 8 minutes left, so there's time for other questions. If anybody wants to raise their hand. Or any last thoughts from Anna and Samantha?
Thanks for listening. We're happy to present this. I think we presented at BLC, so if this is your second time hearing, thanks for joining us a second time.
Yeah, this was really good. Thank
If
you.
anybody wants extra info, please let us know. We're happy to discuss this further. If you want extra details.
Yeah, I agree with that. And then just if anyone, encourage everyone to share any other studies that are similar to this or research they're doing, just because we can all learn from each other. And there's a lot to learn in this space right now.
Awesome. Thank you both. This is a really good study, and I'm glad you shared it with us. And will everybody else have a good day? Well, everybody have a good day, not just everybody else, but thank you all for joining.
Thank you. Thanks a lot.
Bye.
Bye.
Everyone.